Okay, so adding and subtracting radicals, I know, they can look pretty intimidating when you first see them. But what if I told you the secret to solving them is something you actually learned way back in basic algebra? Yeah, it really all comes down to one simple rule, and by the end of this, you're going to see just how easy it is. All right, take a look at this. At first glance, the square root of 50 plus 3 times the square root of 2, they seem like they have absolutely nothing in common. It kind of looks like we're stuck, right? But are we? Just stick with me for a couple of minutes, and I promise you'll know exactly how to tackle this. Here it is. This is the big secret, and honestly, it's a total game changer. If you understand that 3x plus 5x equals 8x, you can totally master this. We're just going to treat that radical part, the square root of 2 or the square root of 5, exactly like it's a variable. Seriously, that's the whole trick. So the most important idea here is what makes radicals like. For them to be considered like radicals, they have to match in two very specific ways. First, the index, that's the little number on the root, which for square roots is an invisible 2. It's got to be the same. And second, the radicand, that's the number inside the root, that has to be exactly the same too. Both parts have to match, no exceptions. This slide just lays it out perfectly. Look on the left. Both terms have a square root of 5. They're like, so we can combine them. Now look on the right, we've got a square root of 5 and a square root of 7. Since the numbers inside are different, they are not alike. We can't combine them. It really is that straightforward. So here is our 3-step game plan for pretty much every single problem you'll see. Step 1, and this is by far the most important, you have to simplify every single radical completely. Step 2 is to look at what you have now and identify the terms that are like. And step 3, you just combine the numbers out front, the coefficients. That's it. Simplify, identify, combine. Let's start with a nice, easy one to see this in action. We've got 4 root 3 plus 7 root 3 minus 2 root 3. Notice anything? Well, step 1, simplifying, is already done for us. They all share that exact same radical part, the square root of 3. So, since they're all like radicals, we can just focus on the numbers out front. We'll group them together. 4 plus 7 minus 2. And that square root of 3, it just kind of cags along for the ride, exactly like an x would in an algebra problem. And the math here is super simple. 4 plus 7 is 11, take away 2 is 9. So our final answer is 9 root 3. See? You totally got this. Okay, you ready? Let's go back to that problem from the very beginning. Now that we have our 3-step game plan, that expression doesn't seem quite so scary anymore, does it? Let's apply our rules and see what happens. Okay, this is where the magic happens. The 3 root 2 is already as simple as it can get, but look at the square root of 50. We can actually rewrite that as the square root of 25 times 2. And we all know the square root of 25 is just 5. So the square root of 50 is really 5 root 2. And just like that, our problem becomes 5 root 2 plus 3 root 2. They were like radicals hiding in plain sight the whole time. And now for the easy part. We just combine those coefficients. 5 plus 3 gives us 8. The final answer is 8 root 2. That problem that looked totally impossible at the start was just waiting for us to simplify it. All right, let's step it up a notch. In this example, if you look at it, none of the radicals are alike, at least not yet. This is where we have to apply step 1 to every single term in the expression before we can even think about doing anything else. Let's break these down one by one. The first term has a square root of 12, which simplifies to 2 root 3. But, and don't forget this, there was already a 2 out front, so we have to multiply them. 2 times 2 gives us 4 root 3. Okay, next up, the square root of 27 simplifies cleanly to 3 root 3. And finally, the square root of 48 simplifies to 4 root 3. And would you look at that? All of a sudden, they have all become terms with a square root of 3. So now we can rewrite the entire expression using our new simplified terms. It looks so much cleaner, doesn't it? We have 4 root 3 minus 3 root 3 plus 4 root 3. This looks just like that first basic example we did. All that's left is to combine those coefficients. 4 minus 3 is 1, plus another 4 is 5. And our final answer is 5 root 3. We just took a problem that looked super complicated and broke it down into simple, easy steps. You know, knowing the right way to do things is great, but knowing where people usually go wrong, that's even better. So let's talk about the 2 biggest traps that students fall into, so you can make sure to avoid them. Okay, this is trap number 1, and it is the most common mistake by a long shot.
It is so tempting to just add the numbers inside the radical, but you absolutely positively cannot do that. The square root of 2 plus the square root of 3 is not the square root of 5. Just remember our main rule. You can only combine the numbers on the outside when the radicals on the inside are a perfect match.
The second big trap is just impatience. You might look at an expression like the square root of 8 plus the square root of 18 and just think, nope, can't be done. But if you skip that crucial first step, simplification, you'll completely miss that the square root of 8 is really 2 rad 2, and the square root of 18 is 3 rad 2. Always, always simplify first. It's the key that unlocks almost every single problem. So you might be wondering, okay, why do I actually need to know this? Well, it has some really practical applications. In geometry, for example, whenever you're trying to find the exact perimeter of a shape that has diagonal sides, think about your special right triangles, the lengths of those sides are often radicals. And to get the total perimeter, you've got to be able to add them up. And believe me, this isn't the end of the road. The skill you just learned is a fundamental building block for what's coming up next. You're definitely going to need it when you start multiplying radicals and when you learn a really important technique called rationalizing denominators. So mastering this now really sets you up for success down the line. So we've seen that by always simplifying first and then just treating radicals like they're variables, we can add and subtract them with total confidence. The process really does turn chaos into order. Which, of course, leads to one last question. Now that you can add them, are you ready to multiply them?